In three-phase systems, loads can be switched either in Y, also known as a star connection, or in delta, like a triangle. In this video we will look to the impact of a Y and delta connection on different voltages and currents. So let's start off with a three-phase voltage system which is always connected in Y. That is because in a delta system, high harmonics can cause extra dissipation in the voltage system. So three-phase systems are always connected in Y. And what we see over here are three voltages, which are separated by 120 electrical degrees. We have EAN, we have EBN, and we have ECN. And these three voltages are phase voltages. They are voltages which with respect to the neutral over here. And we have defined a line voltage, and EAB is a line voltage because it's the difference between the phase voltage EAN and EBN. And when we connect a load to it, and in this case it's a delta connected load with three equal impedances, Z1, Z2 and Z3, we have three phase voltages, EAN, EBN and ECN, and we have three line voltages, EEB, EAB, EAC between A and C, and BC, between the phase voltage EBN and ECN. So what we can do now is we can determine the vectorial difference of two phase voltages to determine the line voltage, for instance voltage EEB. So what we are going to do is we define the voltages as phase vectors in this phase diagram. So EAN is put on the horizontal axis, the phase voltage EBN lags the voltage EAN by 120 degrees, and ECN lags EBN also by 120 degrees. And now we are going to construct the line voltage EAB, and we are going to do that by adding or subtracting, I should say, EAN by EBN. But subtracting a vector EBN is also equal to adding the opposite vector. So we can say EAB is EAN minus EBN, so this voltage is that voltage minus that voltage. But we can put it another way, we can say it's EAN plus the inverted vector minus EBN. So when this is EBN, minus EBN is in that direction, and the adding of EAN plus minus EBN, that vector equals this vector, the line voltage EAB. But now the question pops up, and that question is how big is that vector EAB with respect to that voltage EAN? Or in other words, what is the contribution of the line voltage with respect to the phase voltage? So what is the division of the line voltage by the phase voltage? What factor is in between? Well, what we can do is we construct it by using this graphical approach. And first of all, you should notice that all these phase voltages have the same amplitude. So the amplitude of EAN is equal to EBN is equal to ECN. So these phase vectors have equal length. So when we are going to construct or to calculate this vector, what we can do is we make a rectangular triangle over here. And when we have that rectangular triangle, we can calculate this vector by using Pythagoras. So let's construct this triangle over here, and when we have that, we can add up these two real parts. The two parts are the horizontal axis. We put them to the power of 2, so the square of it. Then we take this vector, we put the square of it, so it's that vector squared plus that vector squared, which gives us EAB squared. So looking to this vector diagram, this phase diagram, we see that this is 120 degrees. So this angle has to be 60 degrees. And when that is the case, this angle is also 60 degrees. So because EAN is in length and amplitude equal to EBN, we can say that this horizontal part is EBN times the cosine of 60 degrees, which is equal to EAN multiplied with the cosine of 60 degrees. And the cosine of 60 degrees is 0.5. So we can do the calculation. We can say EAB is this part, this horizontal part, which is EAN plus 0.5 times EAN squared. Now we have to define that part of the triangle over here. So this is EBN, which is equal to EAN. This is 60 degrees, so this part is EBN or EAN times the sine of 60 degrees, and that is 0.5 times the square root of 3. So now we have the horizontal part is 1.5 times EAN squared plus EBN times the sine of 60 degrees squared, which is equal to EAN times the sine of 60 degrees squared, and then the square root out of it gives us EAB, which is the line voltage. Working that out gives us the square root of 1.5 times EAN squared plus EBN or EAN times the sine of 60 degrees with it, which is the square root of 3 over 2 squared, which is equal to 9 over 4 times EAN squared plus 3 over 4 times EAN squared, which is equal to EAN times the square root of 12 over 4, which is the square root of 3. So EAB is equal to EAN times the square root of 3. So in general, we can say the line voltage over here is equal to the square root of 3 times the phase voltage EAN or EBN or ECN. So it's always a situation that in a Y-connected voltage system, which is always connected in that way, L, so the line voltage, always equals the square root of 3 times the phase voltage. Okay, so in a European system, like in the Netherlands, we have a phase voltage, an RS voltage of 230 volt AC. So the line voltage between two phases is always 400 volt, which is the square root of 3 times 230 volt as a phase voltage. Okay, now let's look to the power and loads, and we can connect the load either in a Y-connected situation or in a delta-connected situation. This is called a Y-connected situation because it equals the Greek letter Y upside down. Alright, so we call it a star or a Y-connected load system. And let's start off with the power in a Y-connected symmetrical load. So here we have our power system, our voltage system, which is always in Y-connected. And here we have a load also connected in Y. So what we can do over now is we have three equal loads, and these equal loads are impedances. Impedance Z over here, Z over here, and Z over here. And in most situations, Z is a combination of resistive and inductive load. It could be, for instance, a motor. And when that is the case, we can make the phase diagram over here, in which we have the phase voltages EAN, EBN, and ECN over here. Here we have the line voltages EAB, which we have defined previously. And we can also draw the line currents, which is EA coming from this phase voltage, which is EB coming from that phase voltage, and IA, IB, and IC coming from the phase voltage ECM. And because this is a resistive inductive load, the currents always lag the voltage. So IA lags the voltage EAN. And the phase angle is the phase angle phi. So IA lags EAN, IB over here lags the phase voltage EBN, and IC lags the phase voltage ECN. The active power in this Y-connected symmetrical load is equal to the power in this load plus the power in that load plus the power in that load. So it's 3 times the power dissipated in one phase. So we are looking to the active power, which is P. So my solution is that the total power is 3 times the voltage, the phase voltage EAN, or EBN, or ECN, they are the same, times the line current IA times the cosine of phi, so the phase angle over here. So it's equal to 3 times the phase voltage times the line current times the power factor cosine phi. So what we also can define is the relationship between the phase voltage and the line voltage as expressed on the previous slide. So we can say E phase equals E line divided by the square root of 3. And in that case we get that Py equals 3 times the phase voltage, which is equal to the line voltage, divided by the square root of 3, times the line current, I line, times the power factor cosine phi. So the total power is equal to the square root of 3 times E line, the line voltage, times I line, which is the line current, times the power factor, the cosine of phi. So that is the general expression of the active power in a Y-connected symmetrical load. Now let's look to a delta-connected symmetrical load. So we have put the load in delta, so this resembles the Greek letter delta, and of course the voltages are still Y-connected. So also in this case we have the phase voltages over here, and we have the line voltages, which are the differences between two phase voltages. So EAB is a line voltage and also ECA is a line voltage. This is my phase diagram, and we have the phase voltages put over here. Now the active power P delta in a delta connected symmetrical load can be defined in a way which is equal to this expression. P delta is 3 times the power in one impedance, so the power in an impedance Z, which is equal to 3 times the line voltage, EAB in this case. Remember, this is the line voltage, which is across this impedance Z, so it's 3 times EAB, or the line voltage, times the current through an impedance, which is IZ1 in this expression, times the cosine of phi, which is the power factor. So we get P delta is 3 times the line current, I line, sorry, that should be E line, times IZ, which is the current in this impedance, times the cosine phi, which is the power factor. So remember, this should be E line. Sorry about that. Well, we have an expression about the total power with the line voltage over here, and we have that strange expression for the current through one of the impedances, IZ. So what we are doing now is we are going to express that current, IZ, into a line current defined here as IA. And what we have defined is also that the currents flowing out of one of the phases is positively when they are flowing out of the positive direction of the voltage source. So IA is in that direction, so also IZ1 is in that direction. IB is in this direction, so also IZ2 is in that direction, and IC is also in that direction, so also IZ3 is in that direction. What we can do now is we can use one of Kirchhoff's laws, which says that the line current IA is equal to the current through this impedance IZ1 minus, because of the opposite direction, minus the current IZ3. So at this point, we can say IA is equal to IZ1 minus IZ3, or we can say it's IZ1 plus the inverted IZ3, so plus minus IZ3. Remember, these are all vectors because we are looking to the phase vectors, the phase diagram. And in that phase diagram, we have defined EAN, the voltage, phase voltage EAN, EBN, ECN, and we have defined the line voltage EAB, which was EAN minus EBN, and we have drawn the phase voltage or the line voltage ECA, which is EC minus EA. What we also see is that we have defined the currents through the impedances Z, and the currents IZ1 lags, of course, the voltage EAB because it's a resistive inductive load. So there is a phase angle phi between the line voltage EAB, this voltage, and the current through this impedance IZ1. That is also the case for the current IZ3, this current, which lags the line voltage ECA, which is this voltage minus that voltage. Now we can work this out. We can do that by drawing IA, which is IA, which is equal to IZ1, which is have a look over here, that one, plus minus IZ3, and that is this vector. So we have minus IZ3, that vector, plus we add to that IZ1, which is that vector, and that brings us with the constructed vector IA, which is the line current I line. So how long is this vector IA, that line current, with respect to the currents through the different loads Z over here? What we can do is we can make a triangle out of it and we define it by taking a squared angle over here and divide this line into equal parts, and then we can say that the complete vector IA, so the line current I line, is equal to that part plus that part. This part is equal to IZ3 times the cosine of 30 degrees, and that part is equal to IZ1 times the cosine of 30 degrees. And remember, the length of IZ1 and IZ3 are the same. So we can say IA is IZ1 times the cosine of 30 degrees plus IZ3 times the cosine of 30 degrees. Cosine of 30 degrees is equal to 0.5 times the square root of 3. So we get it's IZ1 plus IZ1 times 0.5 times the square root of 3. So IA is IZ1 times the square root of 3. So IA is equal to the current to one of the impedances, because it's a symmetrical load, times the square root of 3. So in that case, we can define that IZ, the current through one of these impedances, is equal to IA over square root of 3, or in other words, is equal to the current I line, so one of the line currents divided by the square root of 3. So we can use this expression and that expression, and then we get that the complete power in a delta connected symmetrical load is equal to 3 times E line times IZ times cosine of phi, which is equal to 3 times E line times, well, I line divided by the square root of 3, this expression, times the power factor cosine phi. So again, we see that also the power in a delta connected system is equal to the square root of 3 times the line voltage E line times the line current I line times the cosine of phi, so times the power factor, which is completely the same expression as in a Y connected symmetrical load. So both in a Y connected symmetrical load as in a delta connected symmetrical load, the power, the total power in that load is equal to the square root of 3 times E line, the line voltage, times I line, current, times the power factor, the cosine of phi. The only thing is, the question that pops up is I line for a delta connected load equal to I line in a Y connected load? Well, it's not, and I'm going to prove that in the following slide. This is my Y connected load, and that is my delta connected load. We have seen that the total power in my Y connected load is the square root of 3 times E line times I line times the cosine of phi. And we have seen that I line is equal to E phase. I line is E phase divided by the impedance Z. So again, this is purely one phase voltage over here. So this can easily be calculated by using Ohm's law. You can say I line is E phase divided by Z. Now let's look to the delta connected load over here. Again, we have defined that the total power is equal to the square root of E line times I line times the cosine of phi. But I line in a delta connected load is the square root of 3 times one of the currents through one of the phases. So it's the square root of 3 times the voltage across that load over here, which is the line voltage, E line, divided by the load itself, the impedance of the load Z, which is equal to the square root of 3 times, well, E line is equal to the square root of 3 times the phase voltage E phase, so it's square root of 3 times E line, which is the square root of 3 times E phase, divided by Z. Well, the square root of 3 times the square root of 3 equals 3, so we get I line in a delta connected load is 3 times the phase voltage over the impedance Z. So compare that to the line current in a Y connected load, and we see that the line current in a delta connected load is 3 times higher with respect to the line current in a Y connected load. So conclusion, the line current in a delta connected load is 3 times the line current in a Y connected load, so also the power, which has the same expression in a delta connected load, is 3 times the power in a Y connected load. And that's why often motors which are connected in delta are switched up by using a Y delta switching unit in order to reduce the inrush current. So last but not least, let's have a brief look to the systems which we have at home, in which we have 3 phases over here, 3 phases which have a phase voltage between one of the phases and the neutral over here, and which are equal to an affected or RMS voltage of 230 volt AC, of course. And the line voltage in our system is the square root of 3 times 230 volt, which is 400 volts. So these are the line voltages. What we also do in a home situation that we not only have the neutral fed out to our sockets, but we also have an earth pin connected for safety purposes over here. So what do we find at home? Well, the phase voltages have always a brown wire. The blue wire in our home systems is always used for the neutral, and we have that famous yellow-green wire which is connected to the protective earth, so to the earth pin. Well, that's all about Y and delta connected load systems. Thank you for watching.